Hi folks, this is Physical Science Module 15 Study Guide. Both of the definitions are probably going to be on the test, so I would learn those both. Number 2 says, explain, and please do these on your own before you watch the video and then correct them based on the video. Number 2 says, explain the wave theory of light, the particle theory of light, and the quantum mechanical theory of light. So this is a three-part question. If you have a question like this on the test, make sure you answer each part individually. Maxwell describes the wave theory of light, right? Light is an oscillating electric and magnetic field, right? So it's like a wave oscillating a field. The particle theory of light. So Newton described light as packets of particles, or photons, which we now call them, that move in one direction. And the quantum mechanical theory of light. But this tells us that light is an electromagnetic wave that is also made up of discrete packets of waves that contain an exact amount of energy, and those are called photons. So you want to make sure with quantum mechanical theory you say wave-particle duality and photons. So number 3, or light is a packet of wave. Number 3 says sound waves cause air to oscillate. What do light waves oscillate? So light waves oscillate an electric and a magnetic field. And that's why they can travel through space without a medium. They oscillate a field that's present even in the vacuum of space. Number 4, what does Einstein's special theory of relativity say about the speed of light? So Einstein's special theory of relativity tells us that light speed in a vacuum is the cosmic speed limit, and nothing can go faster. So at least for particles with mass, nothing can go faster. And also nothing can go faster than light in any given substance. So if we're traveling, say, instead of in a vacuum, in water or in diamond or whatever we're traveling in, light is always the fastest thing. Let's see, number 5. Light is traveling through water and suddenly breaks the surface and enters air. Did the speed of light increase, decrease, or stay the same when it leaves water and enters air? Okay, so light always slows down when the medium gets, we'll say, denser for you guys, and it speeds up when the medium gets less dense. So air is less dense than water, and so when light goes from water to air, it will speed up. The speed will increase. Number 6, order the following colors in terms of increasing wavelength. So increasing wavelength means start with the smallest wavelength, that's the 400 nanometer end, the violet end, and then move to the biggest wavelength, the red end, or the 700 nanometer end. So closest to the purple end, we have violet, and then green, and then yellow, and then orange. Number 7, order the colors and problem 6 in terms of increasing frequency. So, right, we're going to start with small frequency and go to big frequency, right? So that would be exactly backward, because where frequency is big, wavelength is small, and vice versa. So that would be orange, yellow, green, violet. Number 8, do radio waves have higher or lower frequencies than visible light? And what about X-rays? So 2-part question. Make sure you read carefully on the test for these. So do radio waves have higher or lower frequency than visible light? So radio waves, remember, they have that 10-meter huge wavelength. So big wavelength means small frequency, right? Radio waves have a small frequency. And then X-rays. So X-rays have teeny wavelength. And that means they have big frequency. So X-rays have big frequency, and radio waves have small frequency. Number 9, infrared light is given off by any object that is losing heat, right? So I'm giving off infrared radiation right now because I'm losing heat to my environment. The human body is almost always losing heat to the environment. Why then do we not glow at night since we're emitting light? Well, the answer is we do. We just can't see it because it's not within the visible spectrum of the human eye. But some creatures may be able to see infrared wavelengths, or we could use camera equipment to show infrared wavelengths being given off. So yes, you glow. You just can't see it. Number 10, light hits a mirror, making an angle of 15 degrees relative to a line perpendicular to the mirror's surface, or we would say 15 degrees relative to the normal line. Why, oh wait, that's the next question. What angle does reflected light make with the same line? So remember our law of reflection. The angle of incidence equals the angle of reflection. So if the angle of incidence is 15 degrees, then the angle of reflection will also be 15 degrees, right? Here comes in at 15 degrees with the normal. Here's the normal, right? If we come in at 15 with the normal, we go out at 15 with the normal. So 15 degrees. Number 11. Oh, here's the one that I was talking about in the lecture. In the following diagram, will the man see his foot despite the fact that the mirror is not as long as the man, or it doesn't reach the ground? So it's a flat mirror. It's not going to distort the image, right? And so hopefully you said yes. In a flat mirror, it only needs to be half your height so that you're able to see your foot. Right, so in that case, here's the mirror, here's the man, right? Oh, that's like a terrible man. He's got a tail. Okay, so he can see hopefully the top of his head. He can see the bottom of his foot. The angle of incidence equals the angle of reflection for both of those, right? So we actually don't need this piece of the mirror. No light rays that hit it would strike his eye anyway. We only need a mirror that's about half his height if I could draw. So, number 12. When light rays travel from one substance to another, what two things can happen to the direction of the light rays travel? So when you're changing substances, you can have rays that refract or enter the other substance and bend because it's a different substance and they change speed, or they can reflect, right? So light rays can refract or reflect, or both can happen at the same juncture. That's kind of why when you look in a window, you can see what's outside because light rays come in and they refract. And you can also see like a dim image of yourself, like a little bit of a mirror in the window. And that's because some light rays are reflected and bounce back to your eye and you see your own image. Number 13. In a physics experiment, a light ray is examined as it travels from air into glass. If the angle the light ray makes with the line perpendicular to the glass is measured, will the refracted ray bend toward or away from the line? So remember the rule we learned in the lecture. When light rays slow, they bend toward the normal. So it's going from air to glass, so it's going into a denser medium. The light will slow, and so the light ray will bend toward the normal. Number 14. When you look at objects underwater from above the water, they appear to be at a different position than where they actually are. Why? So light bends at the juncture made between the water and the air. And you want to know which way. Look at figures 15.7 to avoid me trying to draw it badly. Just examine 15.7 in your book, and that figure will help you out with this. And we will look at a couple of things in the lab that will also help out with this. But light bends so that when you look at the water, well, maybe I'll try to draw it. All right, so I've tried to draw it. So here's our eye, which is awful, I'm sorry. And as the light beam comes from the object up to our eye, right, what actually happens is the light comes and it bends toward our eye from the object. And it bends as the light exits the water, it bends then away from the normal, right? But our eye thinks light always goes in a straight line in our experience. So our brain perceives that the light has gone in a straight line. And so objects will appear to be shallower and nearer than they actually are when they're underwater because we perceive that the light rays go in a straight line when in fact they bend when they leave the water. So hopefully that helps. The object should appear shallower and nearer to us than what it actually is. So this is the actual object, and then this is the object that where we perceive it to be, shallower and nearer than it actually is. Okay, so number 15. In order for you to see a rainbow, what 3 conditions must be met? So you have to have white light source behind you. So you'll see a rainbow when the sun is behind you and you're looking forward at the rainbow. Water droplets need to be in the air, and they need to be up high in the atmosphere and low, like the water droplets need to be dispersed in the atmosphere. So that generally needs to have rained or be raining in the distance in front of you. And then the sun has to be at a certain angle, somewhere around 40 degrees is ideal for you to be able to perceive a rainbow. So you might see one in the sky, you might see one from the mist of a waterfall, from the garden hose, but those 3 conditions are required for you to see a rainbow. Number 16. What is the difference between a converging and a diverging lens? So a converging lens will have light rays focused down to one point. A diverging lens will have the light rays bend away from each other. And I am 17. Which one is converging? Which one is diverging? I will draw those and kind of show you how they bend the light rays. Okay, so a converging lens looks like figure A on number 17. And so all the light enters and then focuses down to one point. And a diverging lens looks like figure B. Light enters, but then it moves apart. Light enters, moves apart, light enters, moves apart. And so the light rays that exit the lens bend all away from each other, or they diverge. Number 18, what is special about the way the eye focuses light compared to the way a camera focuses light? So the eye's lens actually changes shape and the muscles stretch and squish it to cause it to focus, whereas a camera's lens changes position to focus it. Number 19, suppose cone cells, so cone is for color, CO, on your retina sense red light stop working. If you look at a white piece of paper, what color would it appear to be? Right. So if your red cones have stopped working, then you will see when you think about the additive primary colors, you have red, blue, and green. If you can't see red anymore, then the 3 can't come together to make white light. So you'll see blue and green, and a combination of blue and green is the color we call cyan. So you would see cyan. If you looked at a red piece of paper, so this is another 2-part question, don't be fooled. If you look at a red piece of paper, but your red cones have stopped working, then the only light being reflected back to you by that red piece of paper is going to be red light, and you can't perceive red light without your red cones. So you would think that that piece of paper was a black piece of paper because no colors of light were reaching your eye. Number 20, a shirt is dyed so it looks violet, so subtracted primary colors because it's a dye. What color of light does the dye absorb? So if you see that shirt is violet, it's reflecting only violet back to you. It's absorbing every wavelength except for violet. So it absorbs every single color but violet. Number 21. A cyan dye is made of a mixture of substances which absorb all light colors except blue and green. If you look at a cyan piece of paper and place it in a dark room and shine a red light on it, what would you see? So would a cyan piece of paper reflect red light? So no, it reflects only blue and green. It will absorb red light if it's a cyan piece of paper. So all the light shining on it would be absorbed, and so it would appear black because it's not reflecting any light. What would happen if you shined a green light on it? Well, a cyan piece of paper can reflect green and it can reflect blue. But if the only light available to be reflected is green, then it will appear to be green. And hopefully, my lab works on film, you will see that in the lab. So that's the end of the study guide, and I'll have a lab video hopefully shortly.